Welcome. We started with some matrix methods to use for the solving the model equations we obtain, and we started with the methods which can give us the solutions without any iterations, and that were LU decomposition and the tri-diagonal matrix system. Now in this lecture we shall be going further with a few more methods, and in this lecture we shall be covering both the direct methods and the iterative methods. So first let us Gauss-Jordan method, which is a modification of the Gauss elimination, and it is often used to find out the inverse of a matrix, and in this case we use an augmented matrix, and this particular method I shall be illustrating you with an example. So here we see that we have a set of equations with the three variables x1, x2 and x3, and these equations have to be solved to get the value of x1, x2 and x3. So let us first put this set of equations in terms of the matrices. So you have this A matrix of the coefficients, and the X matrix is the unknowns, the vector, and B is the vector of the forcing functions. Okay. Now what we do, that after this thing we make the augmented matrix. What we do, that we put another matrix. In this we put the values of A first, and the last column we put all these forcing functions over here. Now what we do, that we first normalize the first row by dividing with the pivot element. Pivot element are the elements at the diagonal. So if I divide the first equation with the diagonal element, we get this particular thing, and a second equation we divide by the 7, so we get this thing, and the third one we get this. Now you see that we are trying to reduce the whole system into that we want to have a upper triangular matrix. So we are doing what, that R2 and this is going to R2 minus 0.1 into R1, so that we are getting this as 0. So this way we are able to slow one by stepwise we are able to get the zeros at the lower triangular thing. So this we continue. Okay, this is also done in the Gauss elimination method. In Gauss elimination we also convert the parent matrix into an upper triangular matrix, and then we go do a backward sweep to get the values of the unknowns. So same thing we are doing. Now here what we are doing, that as in a Gauss elimination we are also making all these diagonal elements to be 1. So once we have done this thing, you can see that we have converted the parent equation into an identity matrix. Identity matrix, you can see that in which the diagonal elements are 1 and all the super diagonal elements and the sub diagonal elements will be 0. So we have getting the identity matrix, and when we get the identity matrix, now it is very easy for us to solve for the unknowns. So we find that x1 will be equal to 3, x2 will be equal to minus 2.5 and x3 will be equal to 7. So this way you can carry out this particular method, and you can also program it to get the solution. But as I was telling, that it is not always possible to use these direct methods, and they prove inefficient as the dimension of the matrices become larger. So we go for indirect methods. So now I shall be going to some of the indirect methods. And one thing I must tell you, that whenever you are, for actual systems, whenever you are linearizing the equations, many times even without linearization also we start with nonlinear equations, in the sense that suppose I have an equation like this. So I have an equation like this, that A11 say x1 square and say A12 x2 square, and suppose A13 x3 square equals say B1. So this is just illustration. Okay. In many times what we do, if it is non-linear, we can take this x1 into x1 and then 1 2 x2 into x2 and then 1 3 x3 into x3 equal to B1. So you can see here these coefficients are themselves function of the unknown. So this is also one way of treating these things. But when you do this kind of system, then what you see, that you have to go for iteration, because you start with some guess value of x1, x2, x3, so that you can find the values of these coefficients, and then you solve for the x1, x2, x3, and again you modify the coefficient values, and again you get a modified update the value of the x1, x2, x3, and this you keep on doing till you get convergence by checking the values of x1, x2, x3 in the 2 consecutive iterations. Okay. So, that means we are able to stay within this Gauss-Jordan system, but in a iterative manner we are using this system. So, now we shall go to another set of solutions which are purely iterative. So, here we have the Jacobi method, and this Jacobi method, you can see that it is a method which depends on the reorientation or rewriting the given set of equations in terms of each of the unknown variables. That means, if my parent equation is like this, okay, now what we shall do is this: we shall be finding the values of the x1, x2 up to xn from each of the equations. Now, suppose we choose that first equation we shall be choosing to get the value of x1, the second equation we shall be choosing to get the value of x2, and so on and so forth. Now, this choice of the equation to get the value of the given unknown is arbitrary, and there are some mathematical conditions which are prescribed to get those conditions. So, whatever those things, I am not going to those details, but sufficient to say is this: we find these values of these, say, unknowns from each of the equations. So, for example, we want to find the value of x1 from the first equation. So, we write like x1 is equal to b1 minus all the other terms which appear in the first equation divided by a11. Okay. And you can see here that because none of the values are known, we have to start with some initial guess values. So, update the value of the x's. Okay. So, here you see that we are getting x1 k plus 1. So, this k tells us the level of the iteration. So, suppose k is 0, k is 0 means our initial guess values, from that we can update the value of x1. Okay. And now we can see that if we apply this same thing to all the other equations, you find that we can get the value of xi for all the other equations, and this I goes from 2 to n. And in this case we find that as long as we are finding the x1 to xn values for at a given iteration level, we are not changing the values of the x. So, here you see that we are sticking to x1 to xn, we are sticking to the same values of x which we guessed earlier. Okay. So, and then once we have obtained all the x's, then again we start with the second iteration, and again we put all the x values at the second iteration to get the values of x for the third iteration. And before we move on to the next iteration, we must check the values of x at kth level and k plus 1th level, and then if we are not getting convergence, and the convergence criterion will be decided by the user. So, there could be one criterion or more than one criterion. So, that will be decided, prescribed by the user. So, whatever it is, so we have to keep on checking the iteration and to update the values of x. Now, this Jacobi method was found to be less efficient. So, a modification was done, and that we got the Gauss-Seidel method, which I shall be talking about now. In this method, okay, first let us see the example problem here before we go to the next method. So, here we have the set of equations. These equations are the same as the one we have just solved using the Gauss-Jordan method. So, here what we do that we are writing this x1 k plus 1 in terms of x2 and x3, and then x2 k plus 1 in terms of x1 and x3, and x3 from in terms of x1 x2. So, this x1 obtained from the first equation, x2 maybe from second equation, and x3 from the third equation. Okay. So, here you see that we are getting the values of updated values of the x1, x2, x3 by keeping all the values of the x's static at the kth level, and this is the how we are getting the updation. And with this updation, now we can go for the next iteration and we get these particular values. Okay. And again we check for the convergence, like we are taking the what is the fractional change okay, or the percentage change, we see that how much percentage change is occurring. So we are finding that it is giving 12.7% for the x1, then for the x2 it is giving 10.8%, and for the third one it is giving 1.9%. It shows that by choice of the particular equation for x1, x2, x3, x3 is giving the fastest convergence and the x1 is giving the slowest convergence. Now you can see that if we want to make the rates of convergence for each of the variables faster or of the same magnitude, then we can again change these orders of the equations to obtain or to update the values of x1, x2, x3. So this is one example that in this particular choice of x1, x2, x3 expressions, we are getting this kind of rate of convergence, but a different choice of expressions for x1, x2, x3 will give us a different rate of convergence. Okay. So this we can carry on and to get. Now let us go to another method which is a improvement of the Gauss-Seidel, and you see that improvement comes that when we are writing these equations for the first unknown, that is x1, we are using all the variables which are there for the previous iteration level. But when we go for the ith value, you see this is the ith x, then what we are doing, that we are using both the updated values as well as the previous values. Updated values for those which we have already updated, and the previous values for those which are yet to be updated. So we are seeing that for j equal to 1 to I minus 1, that is I, this is I. Okay. So this I plus 1 we are doing the updated values, and which are I plus 1 to n we are doing for the previous values. Okay. Now when you are doing this, we are finding that the rate of convergence gets speeded up. Okay. So this is the advantage we are getting for the Gauss-Seidel method. Now this is the same example we are taking for the Gauss-Seidel method, and we see that how we are doing it, that for x1 again we take the same first equation to get the value of x1, and here is it is that we are finding the x1 value. So once we have got the updated the x1 value, what we are doing, we take this updated value to get the value of x2. So we are putting the updated value of x1, but for x3 we are taking the same value as in the previous iteration. Okay, and we update the value of the x2, and after that for the x3 we take updated values of both x1 and x2. So here we have that we are getting the x1, x2, x3 values for after the first iteration, and these are the values of x1, x2, x3 for the after second iteration. Now you can see that in this case that this rate of convergence of the x3 is the largest, and all of them, if we go on repeating this thing, we will find that x1, x2 will also go at a faster convergence rate than in case of the Jacobi. Now what happened that because the Gauss-Seidel method was showing a better convergence characteristics than the Jacobi method, so and it was also easy to implement in the computer, so we found that the Jacobi method was almost abandoned, and this Gauss-Seidel became the popular method. But what happened later, that when the parallel computing came, this Gauss-Seidel method seemed to be not that efficient, because this is a sequential method. You cannot get x3 or x4 unless you have the value of x1, x2. Okay? So it's a sequential method. But when parallel computing came into picture, then what we found that if you use Jacobi method, then each of these equations can be given to each of the CPUs, and you can get the values of all x1, x2 up to xn together. Okay. So due to this parallel computing, this Jacobi method again got revived. So you are going from a sequential calculation to a parallel computation. Okay. So that is why you find at present day, when if you are go for parallelization and if you are parallel computers, then you will like to go for the Jacobi kind of method, and if you have a sequential thing, then you go for the Gauss-Seidel kind of method. Okay. Now after we have learnt some of these equations or matrix methods to solve the equations. Another important thing is the relaxation factor. Now, the concept of relaxation factor comes in order to speed up the convergence. Now, you see that many a times that if we know the direction of my solution, if we can find out, especially if we are going for a linear solution. So, if we know the direction of our solution, then we should be able to take a larger step size. Okay? That means we can be more adventurous in leaping towards the exact solution. So, whatever updation we are getting, that we can still update further arbitrarily to go reach the solution. And what we define that we always take the difference between the values of the previous and the present time step. So, this is the kind of error you can see. So, if I look at the error, basically all these methods are depending on the error. We are putting some error for, and this error is taken as the value of the xi at k plus 1th level and value of the xi at the kth level. Okay. Now, you see that once we do this, now that means xi k plus 1 is equal to xi k plus this error which we are finding at the k plus 1th iteration level. Now, if we know the direction of our solution, okay, suppose I put this in a graphical form. Suppose we are solving for say versus t, and suppose this is the solution we know, we have to reach here from here. So, suppose by our step size we are doing from here to here we are reaching, okay, one by one. Okay, but now we know that because it's almost linear, what we can do that suppose even if we go to this point, we can take a push this point further on this side, okay, and that we do by taking some multiplying factor so that I can push this solution further, so that I can after this same iteration I can go directly to this instead of going from this to this. Okay. So, this is the principle. So, we are using some arbitrary factor what we call the relaxation factor, which is kind of pushing my solution towards the actual solution. Okay. So, this kind of leaping, it is taking a jump from the exact value which we have got from the equations. Okay. Now, this is the case when we are talking about the linear solution, but this thing cannot be applied if we are going for a non-linear problem. There you find that if there is slight changes here and there, it can cause a sudden, we can move away from the solution. So, whatever delta x or the corrections we are getting at a given iteration level, we may find that applying that whole correction may take us away from the solution or cause divergence. So, in that case, we have to be more restrictive. Okay? So, instead of taking the whole jump to that particular point, what we shall do? We shall take a small jump. That means, whatever corrections is being offered by solving the equations, we shall take less than that correction. So, we are getting more conservative. Okay? It is something like this. Suppose you are walking in a particular room with almost blindfolded, okay, and you know that the room has many furniture scattered here and there. Now, before you have been blindfolded, you know that perhaps that you have seen the place where you have to reach destination. But once you are blindfolded, you do not know where the all the furniture are scattered. Then what you will do? You will be a bit more cautious. So, even if you know the direction of your solution, you don't want to jump around too much here and there, because you know you are going to hit some furniture and you may not be able to reach that. So, you will take smaller steps and slowly you will move towards the destination, and once you know that you are reaching their destination, then you can take a faster step size so that you can reach the destination quickly. Okay? But on the other hand, suppose you have no barriers on your path, okay, you know that if you, then what you will do, you decide that you can take a longer step or faster step to reach your destination. So that is the way we decide that when we need to be conservative or when we can be more adventurous or bolder to choose this particular reduction factor. So you see that in this example, if we take the standard Gauss-Seidel method to give us the solution, it need not be Gauss-Seidel, it can be any other method, it can be Gauss elimination or any other method. So you see that when we find that this kind of things are there, so we first evaluate the solution from the Gauss-Seidel method, and this is the solution we have for the previous iteration level. Okay. Now what we do that to make the exact value of the particular unknown, what we do that instead of the Gauss-Seidel, what we take a reduction factor over here W. Okay, we take the W factor we take here, and with W factor we put with this Gauss-Seidel method, and we take with the value we have obtained in our earlier iteration. Now you see that when W is equal to 0, what it means is this: we are not taking action on the present value. So this whole weightage is being given to the previous value. And when we take this W equal to 1, that means that we are not giving any weightage to the previous value, we are putting whole weightage to the one we have obtained from the particular solution with any given method. But if we take the W value between 0 and 1, that means we are giving weightage to both the present value we have obtained and the value we have taken from the previous iteration. Okay. Now you see that depending on the value of the W, we can have over relaxation or under relaxation. Over relaxation means generally if we take the correction factor more than 1, then we say it is over relaxation. Okay. And if we take the correction factor less than 1, then we say we are going for under relaxation. Over relaxation is generally prescribed if the problem is going towards linear problem, and we go for under relaxation if the problem is more non-linear. Okay. So so this is the way we are able to kind of artificially we try to ensure convergence of the particular set of equations. Okay. So this is the significance of the relaxation factor. The choice of the relaxation factor is arbitrary. Okay, and you need to do some kind of experimentations while you are solving the equations to arrive at the right value of the iteration relaxation factor. And what also happens is this: as you go on iterating, you will find that you may have to tune this relaxation factor to get the convergence. One more thing sometimes researchers do is this: they find the best solution kind of by optimization of the reduction factor. So you see that how much error you are getting in between the previous iteration and present iteration, and you try to minimize this error by optimizing the value of the reduction factor. So the choice of this factor may be arbitrarily or may be done through some optimization depending on the problem at hand. So that is how you see that this particular factor assumes a great importance in the solution, numerical solution of these equations. So more on this you can find in these references. Thank you.